Hello. So, in this video, we're going to be kind of revisiting a previous topic. So, much like when we, looked at the quotient rule, right? We had it initially, and then we did some more work, and then we came back and had another way of doing it. We're going to do something similar here. So, it's sort of a common thread in math. You get sort of more and more advanced tools. You can go back and sort of remake or sort of discover new powerful results in a previous area that you looked at. So in this video in particular, we're going to be introducing L'Hopital's rule. So L'Hopital's rule, this is a way to determine the value of an indeterminate limit for certain indeterminate forms. So as usual, we'll sort of say the full theorem in math speak, but then I'll translate it into human speak. So L'Hopital's rule says if we have two functions, f and g, they're real value functions, and they're differentiable, and suppose that there's some value c, some real number, so that either both of the limits, right, of as x goes to c, both of them are 0 for f and g, or the limit as x goes to c for f is some plus or minus infinity, and the limit as x goes to c for the g of x is also plus or minus infinity. So if you have one of those situations, then the limit of the ratio is going to be the same value as the limit of the ratio of the derivatives. So in human speak, essentially says that if you have some indeterminate form that's 0 over 0 or plus or minus infinity over infinity, then instead of doing some clever algebra to try to sort of resolve the 0 or the infinity, you can instead take the derivative of the top and the bottom sort of independently, and then that ratio will still be the same as the ratio of the original. So it's another way of calculating the limit instead of trying to do some algebraic tricks. So this result should be sort of surprising. I mean, like, why would it be that the ratio of the limits is the same as the ratio of the derivatives? But sort of one of those situations, right, where again, if we sort of look at just the algebra, it doesn't necessarily, there's not a lot of intuition there, so it's sort of easier to think of the geometry involved. So the reason why, and this is a very powerful tool, right, and it's powerful enough that it gets a name attached to it. So this original theorem was written by, sort of maybe surprisingly, not a guy named L'Hopital. So this is originally proven by Johann Bernoulli. But like most mathematicians of his era, he was not particularly wealthy, so he had to have patrons, which is where L'Hopital came in. So L'Hopital was a mathematician. He did eventually prove some stuff on his own that was pretty notable, but sort of to get into the field, he ended up essentially paying Johann Bernoulli to take that result and put his own name on it so that he would become sort of famous enough that he would have enough credibility to start doing his own work. So to this day, we still call it L'Hopital's rule, although some people call it Bernoulli's rule. But really, Johann Bernoulli was the one who invented it. In fairness, he also did a bunch of other stuff he's famous for, so, it's not like he went into obscurity, but there you go. Okay, back to the comment at hand, though. So as mentioned, this is one of those things where the sort of analytic aspect, the algebra, maybe doesn't make clear what's happening very well. So we're going to sort of try to get some geometric intuition to understand what this is actually telling us by a little animation. So we're going to do that next. Normally, when we are considering a limit of f of x over g of x, when both values go to nice numbers and we get a fraction, we simply think of the limit as that value. But when the values go to less concrete values, and we get something like 0 over 0 or plus or minus infinity over infinity, it helps to return to the idea that we're looking at a ratio of values. Looking at our f of x and g of x, we can see that the whole occurs where both are going to 0, and as x gets larger, both f of x and g of x appear to be getting larger and larger. Yet the original f of x over g of x has a hole at a non-zero value, And despite both functions getting infinitely large, the ratio appears to be going down toward 3, and this seems counterintuitive. Let's start by looking at the point where both functions are going to 0. And by looking at, I mean looking very, very closely at. It can be difficult in this context to think about the ratio of values since they're both going to 0. So ultimately, the ratio at the point of interest is, by definition, 0 over 0. But remember, the limits are all about what is happening nearby the point of interest, not at the point of interest. So, with that in mind, let's take a look at just before and just after where the functions are 0. Now remember, we're after the ratio of values. So a good way to conceptualize what we are after is to think, how many times bigger is f of x than g of x as we get near x equals 2? If, for example, f of x is about 3 times bigger than g of x, then f of x over g of x would be about 3. Now, we run into a problem. How do we know if the spot we chose is representative? Even worse, if we try to get closer to the x equals 2 value, we keep coming back to that same 0 over 0 issue. This is where the clever idea comes in to help us. We're thinking about how many times larger f of x is than g of x, but we actually want to know this value as we limit toward x equals 2. So where's the clever idea? Notice that in order for the ratio to be consistent as we move toward x equals 2, the values must change at that ratio. Meaning that if the ratio is about 3, then f of x needs to shrink 3 times faster than g of x in order to maintain the same ratio. Like, going from 9 over 3 to 3 over 1 means the bottom shrunk by 2 while the top shrunk by 6, which is 3 times more. But now we're talking about rates. So what we really want to know is how fast f of x and g of x are heading to 0, and then compare the ratio of those rates. In other words, we want the ratio of their rate of change, or derivatives. We've seen the case where both the functions are going to 0. Let's turn our attention to where they're both going to some form of infinity. Fundamentally, we have the same kind of problem here as we did before. We can't really evaluate the value at infinity, since infinity isn't a point. But we need to find a way to think about the ratio of f of x to g of x as x goes to infinity. Again, it's a bit counterintuitive given that both functions are getting infinitely large as x continues to increase. But remember that we're interested in the ratio of the two values. So even though both are getting infinitely large, and indeed the gap between them is also getting infinitely large, the ratio between the two values can, and in this case does, remain finite. Much like the 0 over 0 case, the fact that we are looking at a ratio means that instead of trying to think of the values of f of x and g of x directly, it's better to ask how much faster f of x is increasing compared to g of x. But again, this is emphasizing the rate of growth, and just as the 0 over 0 case, the ratio of growth rates, or derivatives, reflects how fast one function must change relative to the other. In this case, f of x grows about 3 times faster than g of x, which is why f of x over g of x maintains a ratio of around 3 as x goes to infinity. Okay, so what do we do? So we introduced one of the sort of more powerful tools for computing indeterminate forms, this L'Hopital's rule. So L'Hopital's rule sort of applies to a very specific type of indeterminate form, but it turns out that most indeterminate forms we can sort of rewrite into that form, so it's very broadly used. And in fact, this technique is so useful that it often gets overused. So it's one of those things where it becomes such a well-used and often used technique that it tends to get used even maybe when it shouldn't be used. Not that it is not applicable, but it maybe is not as efficient. So this isn't always the most efficient sort of tool to use, and we'll have a whole other video to sort of explain how or when we want to be careful, right? While there might be other techniques that are sort of faster and easier to use for certain situations. Okay, so that is that.